Hello everyone, so today I'll be discussing question number 32 of GATE 2014 set 2. The axial load in kilonewton in member PQ for the arrangement / assembly shown in the figure below is. So we need to find the value of axial force in this member PQ. It's a 2-mark question of fill in the blank type. And for this type of problems, you can refer to lecture series on strength of materials by Professor S.K. Bhattacharya, Department of Civil Engineering, IIT Kharagpur. Let's start with the solution of this problem. So here is the assembly which is given to us, and we need to find the axial force in this member PQ. Okay, so for that, let me first draw the free body diagram. I'll separate these two structures from here, this structure from here Q, and release the force FPQ, because that is the force which we want to find out. So let me draw separately these two structures. So this is the beam and this is the member PQ. So this is P and Q, this is Q, this is R, and we have one loading here at the middle which is 160 kilonewton and at point S. This distance is given to us as 2 meter and 2 meter. Length of this member is also 2 meter. So this is the diagram. As we have separated it from this hinge Q, so we have to make the force which is released. So it is FPQ here and FPQ here. We need to find the value of this force FPQ. Okay, so for solving this problem, we will use one compatibility condition. So the compatibility condition is delta Q of this structure 1, that is the deflection of this point Q in this first structure, which is delta Q1, should be equal to delta Q of this second structure, that is the deflection of this point in the second structure. Why we are using this compatibility condition? Because this ensures that this structure is connected at point Q, because in the original structure the point Q is intact. Therefore we have to use this compatibility condition to find the value of this FPQ. Another important thing for this problem is that we need to neglect the axial deformations in this member PQ. Why? Since axial deformations are very small as compared to the flexural deformations, so we need to neglect them. Another reason for neglecting them is, since here if we will find this delta Q1, the formula for finding this delta Q1, that is the deformation of point Q in this first structure, is PL by AE. That is, P here is FPQ. FPQ, this length divided by AE. Here we are not given the value of this A and E, which is required to calculate this delta Q1. So if this value of A would have been given, then we could use that value here. But since it is not given, so we have to neglect the axial deformations here. And then other reason for neglecting is the axial deformations are very small as compared to the flexural deformations. So here we have to keep in mind that since axial deformations are small, therefore we are neglecting the axial deformation in member PQ. Okay, so now the compatibility equation we will use. So we are neglecting the axial deformation, so delta Q1 is 0. So the finally our compatibility condition which we need to solve will become delta Q2 equal to 0. So using this equation, we will find the value of FPQ. Now let us find this delta Q2, that is deformation of this point Q in this beam, and put it to 0. From that we will get a value of FPQ. So let us draw this beam separately here. So this is the beam Here is the load, which is 160 kilonewton. Here we have our force FPQ. So this structure we can redraw as a sum of two structures. So this plus this. Here is we have this loading 160 kilonewton, and here we have this load FPQ. So this structure can be made as the sum of these two structures. So we will call the deformation, so this is point Q, this is also point Q. So let us call the deformation for this first structure as delta 1 and this as delta 2. So finally the value of delta Q2, which we need to find out, will be equal to delta 1 plus delta 2. So let us find out delta 1 and delta 2 now. For finding out delta 1 here, we will use the standard deflection formulas. Let's make the deflected shape for this beam. So it will be curved till this point of S, and after that it will go as a straight line since there is no loading here. Now we need to find this value, and this is delta 1. So this total length we need to find out. So this length is the sum of this length, let's call it as delta 1 dash, and this length, which is delta 1 double dash. So delta 1 can be found out using delta 1 dash will be PL cube by 3EI, which is the standard deflection formula of a cantilever beam under point load. Okay, so the formula is PL cube by 3EI. So it will be, what is the value of P? It is 160. What is the length here? It is 2 divided by 3 EI, right? Now delta 1 double dash will be equal to theta multiplied by this length. So what is the value of theta? Theta, again using the standard deflection formula, theta will be equal to PL square by 2 EI. That is the value of theta. So what is P here? P is 160 again, length is 2 square by 2 EI. Now let us find delta 1 finally here. So delta 1 will be delta 1 dash, which is 160 cube divided by 3 EI plus 160 2 square divided by 2 EI multiplied by length, which is 2. So finally from here we get the value of delta 1 as 1066.67 divided by EI. So this is the value of delta 1 we got. Now let us calculate the value of delta 2 also. So for delta 2 we have this, again this beam, but here we have this load FPQ. So it is very simple to solve. The deflected shape will be like this. So here this delta 1 will be equal to PL cube by 3EI. So delta 1 here will be, what is P here? FPQ. What is length? Length is 4. Total length here is 4 meter. PL cube divided by 3EI. Now we know delta 1, we know delta 2. We can find delta Q2 as delta 1 plus delta 2. Delta Q2 will be equal to 1066.67 divided by EI. And what is delta 2? Sorry, this is delta 2. So delta 2 is this term with minus sign. Why negative? Because we are considering downward as positive and upward deflection as negative. Okay, so since this load is causing this delta 2 to deflect in upward direction, so it will be minus. So minus FPQ 4 cube divided by 3EI. Now we will use our compatibility condition, which was delta Q2 equal to 0. So if we will solve it, so 1066.67 divided by EI will be equal to FPQ 4 cube divided by 3EI. From here we get the value of FPQ as 50 kilonewton. So this is the final answer we are getting here. So they asked us the value of axial load in kilonewton for this member FPQ. So we are getting the value as 50 kilonewton. So this is the final answer.